You want that ordered pair to be approaching another ordered pair. Try and illustrate it. Cal 1, you have y as a function of x. The domain in Cal 1 was one-dimensional, wasn't it, the domain? And so if I draw you this, and I say, hey, everyone, get closer to A, then you would come in from this side or this side, right? This is the domain. Yeah? That's Cal 1. What we're talking about now, Cal 3, is that this is the domain, right? You're in two-dimensional space. And now approach a point for me. That point right there, I'm going to call it AB. Approach that point and tell me what the function's doing above that. What's going to be the problem? Does anyone see the problem? I wonder if anyone can see it ahead of time here. Which way are you going to approach it, right? With this one right here, there's only two ways to approach this point, right? From the left or from the right. How many different ways can I approach this point? Infinitely many ways. Look, could I come in like this? I could come in along this line, all these points right there, and that would approach that point, wouldn't it? And then I could do this and say, yeah, I'll do a little curve action and then go towards that point. I could do that. Why not? I could come in and curl through like this, right, and approach that point like that. I could do something crazy. I could start like almost like this death spiral into it, like right, and just head into it. There's no longer just two ways to approach the point like there was in Cal 1. And that is a huge problem. Because for the limit to exist, you have to be able to show that it's approaching the function is approaching an L from every possible direction in every possible path, which you can never do. Do you understand that? You can never check every path. You don't have enough time in your life to do that. Now, there is going to be some workaround to it, but I just want you to see the inherent problem that we run into when it comes to functions of two variables. That's a notation. All right, let's move on. I'm probably going to reiterate exactly what I just said here. Big questions, how many ways can we approach it? So I think I just showed you, here's a point I can approach it, right? I can come in any way and see what's happening on the function, right? This is my domain on the ground. This is the function. I can come into that point so many different ways that imagine that on the surface, you're just kind of approaching that point on the surface from all these different directions. Infinite number of ways that we can approach it. For the limit to exist, must exist for every path, and therefore our life's going to suck. All right, so let's try this. We are going to investigate this function. This is my actual function of x right here. And I want to know what the limit is as xy approaches 0, 0. And I'm going to look at several different paths. So we have a couple of paths that we like to always try first. And we're hoping for the best. But let's be clear. If I come in and I do a limit right now and I get an answer of 1, that does not mean the answer is 1 to the problem. That means from one direction it was 1. Then I would have to check every other direction, which is impossible. So what do you think it is that I'm actually going to hope for? I'm going to hope that from different paths I get different answers, right? If I get different answers from different paths, the limit does not exist. So it's easier for us to check that a limit doesn't exist than it is for us to check that it does. What we don't want to happen here is keep on getting the same answer every time we come in from different paths. Because every time we do, all it does is just tells us we need another path, and we're never going to run out of paths. So let's try one of the first paths that you'll want to come in on. Remember, I'm in two-dimensional space. What point am I approaching? I'm approaching the point 0, 0, which is right here. Right? I'm approaching 0, 0. And one path we really like is the x-axis. like back in Cal 1. Let's come in along the left and right hand sides like this. Okay, so we're going to come in like this. That's a path, isn't it? And that line that I'm coming in on is actually the line y equals 0, right? Which is the x-axis, right? So what I'm going to do is I'm going to go to this limit, and I'm going to fix my y value at 0. Not approaching 0. I'm going to fix y to be 0. And I'm going to rewrite this limit. So here's what it'll look like. Limit as x0 approaches 0, 0. Notice I replaced the y with 0. And then everywhere in here, I'm going to replace y with 0. So x squared minus 0 squared over x squared plus 0 squared. Which equals limit x0 approaches 0, 0 of, well, that's just x squared over x squared, right? And what's x squared over x squared? That's going to be 1, right? That's 1. I can reduce this before I take the limit. So this is just going to be, I'll write it one more time. Limit as x0 approaches 0, 0 of 1. And what's the limit of a constant? Just the constant. So we get 1. Okay, so what appears to be happening is that if I were to be looking on the ground and looking at the x-axis and coming in like this, right? Then up on the function, I should be up approaching 1, shouldn't I? Up on the surface. It should be approaching a height of 1. Now, I'm going to show you a picture of all this in a second, but I want you to kind of see it, try and see it mentally before I show it to you visually. All right, so that's 1. Now let's try a different path. Let's try along, how about the y-axis? That seemed like a natural choice for the next one. Come in this way. Okay, so now let's go along the y-axis, which is the equation x equals 0, and do my limit. This time I'm replacing x with 0. So it's 0y instead of xy. And then replace all my x's with 0, which gives you negative y squared over y squared, which is negative 1. Right? Which means at this point I can stop and I can say this limit doesn't exist. Because from two different paths, I was approaching two different values. Understand that? We got lucky. That's the first example. So limit does not exist. That's the conclusion of this. Question? Yes?
So from each path we take, we have to have the same answer? Limit has to be the same.
If the limit is going to exist, then we need to get 1 here and 1 here for every path you can ever come up with, which, again, is impossible. So we're hoping that through different paths, eventually we get them to be something different. If we just keep on getting 1, 1, 1, 1, 1, you're just going to be like, I got to find the path that's going to screw it up, but maybe it is 1. But you can't check every possible. So you're really kind of backed into a corner here. Do you see that? All right, so let's take a look at the visual of this. See if you can make sense out of this visual. Ah, damn it. Okay. All right, this is along the x-axis. So what I'm going to do is I'm going to take the surface out completely, just so you can see what's happening. If you look at it from this side, well, I guess this is okay. Along the x-axis, see that green dot? Yes? The green dot is just the input, and the black dot is actually the output of the function. So do you see as the x value changes, do you see that the z value, the x value moves along. Do you see that the z value is just staying up there at 1? Something happened there. Do y'all see my computer freaked out there for a second? Right there, when I went through the origin, what happened? It tried to plug in the point 0, 0. But you can't, because 0, 0 into this is going to be undefined, right? But if you're getting closer and closer, it looks like that output is 1, isn't it? Do y'all see that? I'm going to come in and bring that surface back in. There's something really weird happening in there. Do you see that little dip in there? Okay? So it looks like from the side, it's almost like a fortune cookie, right? Or something. It's like folded across the top. And you're running along that top edge, and then all of a sudden, at the origin, it drops down, right? It actually becomes undefined. It doesn't drop down, just is undefined. But along that x-axis, it's up there at 1. Understand? No questions? Okay, now let's look along the y-axis. We come in along the y-axis. See, now we're along the y-axis. The green is the input. The black is the output. Notice that the black is below it, isn't it? So it's down there at -1. There's that surface. We were coming along this edge, right? Now we're down along this bottom edge down here. Y'all see it or not? Give me some feedback. Yes? You see it? Okay. So as soon as we had different answers, we were good. So the conclusion is that this limit does not exist since we got different answers from different paths. Now let's take this path, or this new limit. So let's go back to our kind of always proceed this way. Always start with maybe the x-axis, then go to y-axis. Okay, if I'm going to go along the x-axis, I'm going to let y be 0 first, right? This limit's going to be the limit as x0 approaches 0, 0 of, now replace y with 0 in there. And what do you get? On the top you get 0, right? Over what? X squared. Now, are we saying here that this top is approaching 0, or are we saying that the top is 0? Is 0, right? Because I am actually sitting here saying, let y be 0 so that I'm on the x-axis. Not near it, on it, right? If I'm on the x-axis, y is exactly 0, and then the top is not approaching, it actually is 0. And then 0, the number 0 divided by any number would be what? It should be 0 as long as this is what? Not 0. But what are we doing? We're letting x approach 0 without actually getting there, right? So these numbers down here are getting smaller and smaller and smaller and smaller and smaller, never actually being 0, so we never actually have division by 0. So the answer to this is 0. Now, similarly, if we come in along the y-axis, let x be 0, do you all see what's going to happen? You're going to get 0 again. But 0 over what this time? Y squared. You get the same answer. So does that mean that the limit is 0? No. It means that along those two paths, the same thing's happening. So what should we try next? Or what should we do next?
Are we going to do a different path?
Yeah, let's do a different path. What do you want to try?
Y equals -x.
Y equals -x. That's a good path. The one that we usually go to next is the diagonal, which -x might also, it's another diagonal. But let's go with y equals x as our next choice. So we're going to approach 0, 0 along the diagonal. So that'll be y equals x. We call that the identity function. That's called the identity function, back from college algebra. So let's approach along the identity and see what happens. So what I'm going to do is I'm going to replace all my y's with x's. And I'm going to rewrite the limit up here. Limit, not instead of x, y, I'm going to write xx approaches 0, 0 of x times x over x squared plus x squared. So all my y's became x's. What is the top? Top is x squared, so limit xx approaches 0, 0 of x squared over 2x squared, 1/2. Done. This limit doesn't exist. We found a path that made it not happen, right? Understand that? Questions?
So for how long is it?
That's a great question. Until you run out of lead or time. I don't know. Most of the problems on the homework, it's going to happen somewhere in here. But there are some more unnatural choices, which the last example I'm going to do will be a less natural choice. Okay? Sometimes you just have to think about what's happening in here and how you can get things to change by manipulating what x and y are. Okay, good? Let's take a look at this one. This is a function. Do you all have any idea what this looks like? It's a function that if you come in along the x-axis, it's approaching 0. Along the y-axis, it's approaching 0. But if you come in along the diagonal, the function is approaching the value of 1/2. So is it still a fortune cookie? Let's see. It kind of looks like a fortune cookie still. Right? Y'all see that? So let's come in along the x-axis. There's my x-axis coming in. Notice that we're just running along the edge of this graph. I don't know if y'all can see that. Along the x-axis, we're just kind of, there's this dip in the function. We're just kind of running along this edge, right? And it's our z value is always just constant through that. And then we try and come in on the y-axis. The same thing happens. So here's along the y-axis. We get that same edge effect, running along this edge, always staying constant at 0. On the other side, same thing, right? Look at that from the top, running along the y-axis. But now if we try and come in along that y equals x, there's along y equals x. And you can see pretty obviously that we're up on that top ridge now. So we're up at 1/2. Got it? See, this is where we're at a point in the class, and a lot of it's going to be like this the rest of the way. I'm curious to know, as a student, from a student's perspective, how much of this would make sense without that picture? I wonder. Like, would you see it the same way? I don't know. Or would it just be just a limit, and you're just like, okay, how do we calculate the limit? I don't know. To me, I think the visual is just there to help us see how it's tied to something. It's not just like a limit. Okay, so the answer was does not exist. Okay, last one. You want to try? You want to try and go in along a couple of paths. You're good. How many of you see right away along the x and y axis you get the same answer? Do y'all see that right away from looking at it? Because you have x times y squared on the top, as soon as you let x be 0, the top is 0. If you let y be 0, the top is 0. In both cases, the denominators are either going to be x squared or y to the 4th, depending on what you set. So it's going to be very similar to the last problem, right?